Forces on chip formation. When the chip is formed above the shear plane, its motion is just like a rigid body with finite velocity and zero acceleration. Net force acting on the body is zero, and so the resultant of forces acting on it from the tool surface and work surface should also be zero. Chip formation can be explained by Merchant's thin shear plane theory or minimum energy theory. Assumptions under this theory are: workpiece always moves with constant velocity. Tool has its width more than that of workpiece. Contact forces along the clearance surface is zero. Shear surface is a plane surface, and stress formation on it is uniformly distributed. Chips formed are continuous and have no built-up edge. Cutting edge remains a straight line and there is no sideway spread of chip. As shown in the diagram, the forces acting on the tool are tangential forces called as PT, like this is PT. This force is responsible for cutting. PF is feed force, PC is compressive force, and PS is shear force. We have PF here, we have PS, we have PC, and we have PT. 4 forces. P is frictional force acting frictional force acting on the rake face of tool and N is normal force. So I hope this diagram is now clear. Now these forces can be split as P equal to PF cos of alpha plus PT sin of alpha, where alpha is tool rectangle and N is PT cos alpha minus PF sin alpha. So P by N comes to PF cos alpha plus PT sin alpha upon PT cos alpha minus PF sin alpha. Also, mu is equal to P by N, which is equal to tan of beta equal to PF plus PT tan alpha upon PT minus PF tan alpha. So making all necessary substitutions, we get PT is equal to PS into cos of beta minus alpha upon cos of phi plus beta minus alpha, where phi is shear plane angle and beta is angle of friction. So like here we have made values substituted as PS, which is equal to PT cos of phi minus PF sin phi, and PC is equal to PF cos of phi plus PT sin phi. It is also like to be mentioned that PF and PT are horizontal and PF and PT are vertical and horizontal force components. So this is the result for my tangential component, which is coming finally, or the force responsible for cutting. Then we have stress and strain development on chip. If AS is shear plane cross sectional area, then AS can be written as width of cut into thickness of uncut chip. normal stress is equal to PC by A by sine of phi, which comes to PC sine phi by A. Substituting the value of PC, it becomes PF cos phi plus PT sine phi into sine phi divided by area. Shear stress can be expressed as PS by AS. It is equal to PS by A by sine phi. It is equal to PS sine phi by A. Again equal to PT cos phi minus PF sine phi into sine phi by area. Then is depth of cut. Depth of cut per revolution is denoted by T, and chip thickness is expressed as PC. When we were studying about shear plane, like in the previous diagram what we have studied, I'm discussing that again. This was my shear plane. Let its length be expressed as AB. Then this is my chip, and this was my workpiece, and this was my tool. Then we can say that R is equal to T by TC. T is equal to AB sine phi, where phi is this angle, by AB of cos of phi minus alpha. Rearranging we get R into cot of phi cos of alpha plus sine of alpha, it is equal to 1, which means tan phi is equal to R cos alpha upon 1 minus R sine alpha, or phi is equal to tan inverse of R cos alpha upon 1 minus R sine alpha. Chip thickness ratio is always less than 1, means R is equal to T by TC is less than 1. Also, the volume of metal removed is equal to volume of chip. If W, T and L and density are width, thickness and length and density for metal moved, then it should be equal for the same amounts for cut chip, which means R is equal to L by LC, it is equal to TC by T, and it is equal to VC by V sorry, it is this is 1 by R. R is equal to R is equal to T by TC, it is equal to VC by V, it is equal to LC by L. So these are results for chip thickness ratio. So this was all about the details of machining process. Now in next lecture we will move to basic machining operations. Thank you.